Good afternoon. Okay, today is the big day, the last midterm for Chem 1A. All right, you also start a new lab this week. You will do potentiometric titrations. So you will construct an acid-base titration curves. And for this, you need to know how to handle a pH meter and a pH electrode. Please don't break those pH electrodes. They are very, very expensive. And you need to theoretically know something about acid-base equilibria. That's what you're going to be talking about on Wednesday and on Friday, about pH and about buffer solutions. Okay, so today we're going to talk about equilibria. So what's new? Nothing. Yes, there is something new. Before we talked about homogeneous equilibria. Homogeneous equilibria is where you have essentially the two partners, the reactants and the products in the same phase. And we want to talk today about heterogeneous equilibria. That means where the reactants and the products are in different phases. And we use gases mostly, and you use one solid to explain that. So if you have, for example, CO2, we are now familiar, all of you are familiar with carbon dioxide. It can be a gas, and it can be, and you're not familiar with that, it can be in a liquid. It can dissolve in a liquid. It's not liquid carbon dioxide. It can dissolve in a liquid. So that's aqueous. AQ stands for aqueous. So that means there is CO2 gas above the liquid, and it has a partial pressure, and it dissolves in the liquid. And we say, in this case, we say the liquid is water. So it dissolves in water. With this, we can now write a reaction quotient. The quotient is the concentration of the dissolved species divided by the concentration, and this is the partial pressure because we have a gas, of the CO2 gas. This is this equilibrium quotient, and this is this reaction quotient. And if we are in equilibrium, then we have it is equals K, and that equilibrium is a fixed number at each given temperature. You can look those up. For CO2, the equilibrium constant is tabulated, and that means we call this here, if we have gases in equilibrium with dissolved gases in water, we call this the Henry's constant, Kh. Okay, so it just tells you that you have a heterogeneous equilibrium between a gas, and the gas is dissolved in water in a specific liquid. So this would be Henry's law. So we have the concentration, if you go back here, that's the concentration of the dissolved species, and that's the partial pressure. So the concentration of the dissolved species is the equilibrium constant times the partial pressure of that gas that dissolves in water. So if you look at the solubility, we can say this is essentially the solubility of that species in water at a certain, and this is at 25 degrees Celsius. You see helium is not very soluble at all if you have 1 atmosphere of helium above a solution. Argon is a little bit more soluble. Xenon is even more soluble than argon. Nitrogen is not very soluble at all, but more soluble than helium. If you compare this is 0.4 to 0.7. Oxygen is about double as soluble as nitrogen in water. But CO2 is very, very soluble, okay? And ammonia is extremely soluble in water. NH3 forms NH4OH then in water. It reacts with water to form a base. And so you have to have a certain pressure of NH3 gas on top of an aqueous solution, and then it will go into that solution until you have larger than 10 to 4 moles per liter dissolved. So let's do that. We have here what we call an ammonia fountain, and there she is, Karen, our magician here. And so what she does is she has in this flask, she has ammonia gas in there, okay? And she turned it around, obviously. And so now she puts that ammonia gas is here. She puts that over a tube, which is an open tube, a glass rod, which is open, and connects it now tightly with this water here. And we have put some indicator in this water. This water is neutral. Water is neutral. It's pH 7. So this indicator is pH 7, is red at pH 7. That's called the neutral indicator. And so if we put a tiny little bit of water in here, then we can get that reaction started. So, and this is a very, very, it's a reaction where delta G is smaller than 0. So it goes by itself. Now let's see. Let's do that, please. You see that? The gas wants to dissolve so badly that the free energy, the change in free energy, can overcome that pressure differential between here, and it dissolves it here, and now the outside pressure pumps it up here. You see that? And now we have that indicator. It's blue, it's a base, and this is called the ammonia fountain, and this is due to the high solubility of ammonia gas in water. Okay? So that worked very well, especially if I don't do it, then it always works. So thank you, Karen. That was excellent. So there is another possibility, of course. There is carbon dioxide. Carbon dioxide dissolves, if you have pressure on top of water, dissolves in water. And then when you take the carbon dioxide away on the top, then the CO2 comes out of the water. It goes out of the water into the environment. And where can you observe such a process? When you open your soda can, okay? The soda can has a little airspace on top. And this airspace, that's actually a little space on top. And this is filled with CO2, with carbon dioxide, and it's under pressure. It's a very small amount. It's under pressure because you want to buy a full can of soda and not half a can. And so what this does, it dissolves, the carbon dioxide dissolves in the aqueous solution where you have this artificial Coke thing. And so it's in equilibrium at this point. And now you open up the can, you release that CO2, okay? Now the CO2 partial pressure on top is gone. Now you push that equilibrium towards the gas phase. It wants to come out of solution because it's gone on the top. If you look at this equilibrium here, see, you have this in solution. Before you had this on top here, so this was in equilibrium. Now this is gone. Now in order to get back into equilibrium, it tries to make CO2. And so the bubbles come out of the solution, and you have this effervescent feeling, which makes the taste very good. There's nothing worse than a flat Coke, okay? And so what happens, if you leave it open long enough, then all the CO2 will be gone out of the solution and will have come into the environment, and it's a flat Coke, all right? So this works with champagne, it works with beer, and with other carbonated drinks, but some of them are naturally carbonated, and Coke and other sodas, they are artificially carbonated, so they pump that in here. Champagne, of course, is naturally carbonated, and so you don't see any bubbles when you look, for example, at your Coke bottle. You have this humongous Coke bottle, 5 liters or whatever, you look at it, there are no bubbles to be seen because it's in equilibrium. And only if you open up, this little amount of CO2 is released, which is under relatively high pressure, it's released, and then you have disturbed the equilibrium. And after whose principle are we going now? Le Chatelier's principle. We disturbed the equilibrium, we took this away, so it likes to make more of that to gain that equilibrium. However, it never has a chance to gain this equilibrium because we have it open, the container. If you close the container, and if you didn't drink too much of your Coke, sometimes it works. It's not quite as fizzy anymore, but it will build again a little bit of CO2 pressure up on top, so the rest of the Coke will be still nicely carbonated. All right, there's other possibilities to use that. The solubility of a substance in a solution. That does not necessarily have to be an aqueous solution. You could also use the solubility in an organic solution. And this principle is used in liquid-liquid extractions. So what you have a solution which has something dissolved in that. Let's say we dissolve it in water, okay? And would you think if you have polar things, they like to dissolve better in water, or non-polar things? Polar things, very good, you got the principle. Likes go to like. Polar, water is polar, it has a dipole moment, so it will be much easier for water to accommodate the dissolution of a polar substance. So if you have a non-polar substance, it will like more non-polar solvents, like many organic solvents, they are non-polar. So, and you can use this ability for substances that are polar to dissolve in polar solutions, substances that are non-polar to dissolve in non-polar solutions, likes go to likes, to separate, for example, metals from one solution into another one. And these are industrial separation processes, and I would like to show you this with the example of iodine. If I could have the camera, please, and the lights. I think I need to wear some glasses, otherwise the lawyer's going to go after me. It's not about my health, it's just about the law, okay? But never mind. So you have here, this is iodine solution, brown iodine solution, and this is dissolved in water. So iodine, is that polar or non-polar? You should know that. Iodine, I2, non-polar, exactly. It's a perfectly symmetrical molecule. It's non-polar, and we have that in water, so it dissolves, but it likes to be much more in non-polar solvents. So we use a non-polar solvent, and this would be hexane. It's an organic solvent, is non-polar. And so I'm going to put some hexane on top of this here. And what should happen then? It should go on the top. You see there is a little bit of color already. Let's put a little bit more in there. And now I need to push it from the aqueous phase into the organic phase. I do this by shaking. And now the phases are separated. See the phase boundary here? See the phase boundary? That's the aqueous phase, and this is the organic phase. And so it went from here. You see this is lighter compared to this one, to the one on the left. And it went into that phase. Now I could separate them with a separatory funnel, or I could suck off with the pipette, could suck off that supernatant solution here. And then I have it in an organic phase. Now I evaporate the solution. I have the iodine back in this elemental form, okay, or molecular form. So this is used in industrial processes for metal refining, it's very much used for example, for nuclear fuel rods. They are reprocessed. You don't know much about this, but you should actually, but it's not your fault. And so they are reprocessed by getting out the uranium and the plutonium and all the fission products that cannot be used. So you separate the good products from the bad products by doing a series of these processes. So if I would take this off here and put some more hexane on there, then it would become even lighter. And I do this a couple of times, and then I unify the organic solutions, and I have it completely separated out of the aqueous in the organic phase, and then I can handle the organic phase. So these are separations. We have two non-miscible liquids. One is polar, one is non-polar. So it's also a heterogeneous equilibrium, and they don't mix. So the separation is the solubility in liquid 1 divided by solubility in liquid 2, and this gives you a constant for that metal that you use or for that substance at a fixed temperature. And there is only one equilibrium then you can have that would be given as K, and we call this K then the partition coefficient, right? It partitions from one phase into the other. The larger the partition coefficient is, that means equilibrium, the better a separation we get. So, as I said already, the principle here is that hydrophobic solvents like hydrophobic substances and hydrophilic substances like water, like hydrophilic substances. So likes dissolves likes. That's the take-home message. Let's see if you understand. We have a solution that has equal, the same concentration of helium and nitrogen dissolved in the aqueous phase. So it's an aqueous phase, and it has the same concentration, or we compare two. One has helium dissolved and the other one has nitrogen dissolved, and they have the same concentration. I want to know from you now, is the partial pressure of the helium, does it have to be smaller than the partial pressure of the nitrogen, or are the partial pressures the same, or does the partial pressure of the helium has to be larger than of the nitrogen? So here's your answer, actually. And why don't you think about this and give me your answer, please? You need to look on that table here, okay? What does that mean? What does this table signify? That's the first question you have to ask yourself. What does this table mean? So this is nitrogen, and this is helium, okay? There's a 0.4 here and a 0.7. And it says right here, per atmosphere of X. Plenty of seats here. Okay. Let's see how we are doing. That's to be expected. So it's sort of, data now is probably not the same because it has different solubilities. And so the one say it has to be smaller, and the other say it's larger. And the other guy says, E says, oh, I really don't care because we have the midterm today. Or I like to be funny. That's a different story. So now, this is, if I have 1 atmosphere of pressure above, then I have 0.4 molar of helium and 0.7 molar of nitrogen. But I have equal concentrations dissolved in water. All right? Ah! How did that happen? Did I touch it here? Okay. That's not so good. No, it's fine. So there is no answer, actually. The solution is all of this here, so I have to explain it to you. So if you have 1 atmosphere here, you have 0.7 moles per liter of nitrogen and 0.4 moles per liter of helium. Okay? And so helium is monoatomic, nitrogen is diatomic. It really doesn't matter in this case. So in order to have the same concentration, what do you think the partial pressure has to be higher? For nitrogen or for helium? For helium, the partial pressure has to be higher to get it to 0.7, for example. All right? So it has to be, this would be 1 atmosphere, this would be nearly 1.5 atmosphere, okay? More than 1.5 atmospheres, because it's 0.7. All right, with this you rightfully voted C, and you all got it right. That's excellent. So let's give us another one here. Carbonated beverages. We have this famous Chem Coke here, Chem Cola, and it fits very well because colas, they are usually just chemistry, okay? There's water, there's ascorbic acid, there's phosphoric acid, large amount of phosphoric acid, there's caffeine, and a couple of other things they don't tell us, which makes it taste so special, okay? So that's a Chem Cola. Any Coke is Chem, actually, okay? So some of you have experienced this. You bought a pack of beverages, carbonated beverages, in a hot day and you put it in your car, and you come back in the early evening, bought it in the morning, it was 120 degrees suddenly, or during the day I come back, and these cans look so funny. They have these bulges, okay? And so this is obviously an effect of the heat, and it's not the expansion of that little amount of gas you have on the top, okay? It's another effect. Yeah? It's not the heat effect just of the expansion of that gas. It's a very, very different effect. So what would I'd like to know from you now, if I have, so obviously the dissolution of CO2, from this what I just told you, you can conclude that the dissolution of CO2 into the aqueous phase, into carbonic acid, is either exotherm, isotherm, or endotherm. Endothermic, isothermic, and exothermic. Okay? So you remember, you have to have one needs heat as a product and the other needs heat as a reactant. So you look at this way. Maybe you can get the answer for that one. And I try not to give you the solution before you answered it. Good. Let's go for it. You all should know that, actually, okay? This is just a simple equilibrium, and we have done this many times now. We have said if it's exothermic, heat would be a product, and if it's endothermic, you can look at heat, or the heat or energy, as a reactant. And with this, you know in which direction the equation goes, or the equilibrium will favor which direction. This stuff you need to know tonight, okay? Not everything, but this kind of equilibrium you need to know. It might not be heterogeneous, but there may be heat as a product, or so that would be exothermic, or heat as a reactant, it would be endothermic. What would be delta H be if you have heat as a product or exothermic? Negative. Thank you. Okay. So let's see how you did here. There is a slight majority for exothermic, but other people say, no, that's got to be endothermic, okay? Why don't you discuss this with each other, and maybe you can come to one answer, and maybe the right answer even, okay? Please discuss it. Not all at once. I need to start this too. It's not my day today, huh? Okay. Tatiana here? Tatiana? No? She used to be my head TA, actually, and she is now a school teacher, and she wanted to come with her class. And I wanted to welcome that class here, but they found something better to do. Are you ready for tonight? Yeah? Good. As usual, 40 questions, 120 points. All multiple choice. The question is which choice? Yes. Good. We're getting in the right direction. And why is that? Because you're good, that's why it is. So, if the reaction would be endothermic, on which side would I have to write the heat? Reactants. I would write the heat here. So to which direction would I push that reaction? I would put it over there. Would put it to more products. That means CO2 would go more into the aqueous phase, so the solubility would increase again, or would increase in the aqueous phase. Would that make the cans bulge? Would that? No, I don't think so either, okay? Now, if I have an exothermic reaction, heat would be a product, okay? In which direction would I go? In which direction would I go? To the left, okay? What do I make here? Gas, okay? And the gas has nowhere to go. So it tries to pressurize, it will pressurize that can, and the pressure goes quite high because the temperature got high, and so it will bulge the walls of the can, and if you're lucky, it has not exploded. Okay, and let's see our answer. This is our equilibrium, we just talked about it. So if the partial pressure goes up and the equilibrium constant goes down. And now, if I have the dependence of the equilibrium constant as a function of temperature, how does it look if it's exothermic? Does it go down or go up as a function of temperature? Down? Okay. Exothermic goes down and endothermic goes up. You need to know that. Okay, I think that might be very helpful tonight. We have to talk about this many, many times, all right? So this is the dependence of the equilibrium constant as a function of temperature. For endothermic reactions, the equilibrium constant goes up. Of course it has to go up, okay? And for endothermic, it has to go down. All right, good. Yeah, that was the right answer. So did you do a barium? No, you did the silver chloride experiment in your lab, didn't you? Yeah, so the silver chloride wasn't very soluble. So that was a heterogeneous equilibrium. You had solid silver chloride, and in solution you had silver ions and chlorine ions, okay? So this was solution and solid, was in equilibrium with each other. Heterogeneous, not homogeneous, is as we call these equilibria. So let's look at barium sulfate. That's a solid, and it dissociates into barium 2+ in the aqueous phase. These are ions, and these are anions or cations? Cations, okay, they are positively charged. And in sulfate, anions, they are negatively charged. And there's an equilibrium. If I have this, there's a reaction quotient that I can formulate, and in equilibrium, I have an equilibrium constant. So this is, I take the concentration of the product, all right, the concentration of the product, divided by the concentration of reactant. Oh, I made a mistake here, huh? Concentration of the reactant? It's a solid? I didn't make a mistake? Oh, I'm so lucky. Okay, of course, the solid is a pure phase, and pure phases we set as 1. Remember, water is 1, and barium sulfate is a solid, and we set the concentration at 1. With this is 1 here in the denominator, and we have Q is just the concentration of the two partners in solution, and in equilibrium this is K, and this is as a function of temperature, and at a fixed temperature, it's one specific number. There's only one number for barium sulfate, and you look it up in the back of your book or in tables, or you Google it on the net to get at 25 degrees or 298.15 Kelvin to get that K for barium sulfate, all right? And we call this now solubility product. So you have in your jar here, in your Erlenmeyer flask, you have barium and sulfate ions, and it has on the bottom, it has solid barium sulfate. So that solubility product is very, very small. So the equilibrium constant is smaller than 1. when I say the equilibrium constant is smaller than 1, which is favored? Reactants are favored. That means it's not very soluble. Barium sulfate is favored, and you can see that constant is 10 to minus 10. 1/10 of a trillionth, okay? No, a billionth. Billions, I'm in the German system. 1 billionth, okay? A tenth of a billionth, that would be the solubility product. So how do we know what the concentration in equilibrium of this here and that here is? So it has to be, since there is only no molar, there's 1 mole here and 1 mole here, okay? So it has to be the same. So we call this X here. There's X here and X here. So that means this number is X squared. Yeah? That's this concentration times this concentration times this concentration is 1.1 times 10 to minus 10. So what do you think the concentration of barium or of sulfate by itself is? It's the square root of it, okay? X squared is 1.1 times 10 to minus 10, and I take the square root, then I get just that concentration here. So it's about 10 to minus 5 molar. This is not very high at 25 degrees. It's a very low concentration, 10 to minus 5 molar. So now I'm asking you a question, and this is aiming at the common ion effect, and you have all read about this in your book when you prepared so well for this lecture here today. And so I have a speck, 1 milligram of barium sulfate, and I want to dissolve that, okay? So would I use 0.1 molar sulfuric acid, H2SO4? That would be answer A or 1. Or would I use 0.1 molar barium chloride? That's also very soluble. That's very soluble. That's very soluble. Would I use that, or would I just use water to dissolve it? What would you do? Why don't you think about this and give me your answer? Please. It's called the common ion effect, which is hidden in here, which is also related to Le Chatelier's principle. What shall we use? What would you use? I stunned you, huh? You haven't read it in the book because it's not in the test today, of course. Okay, so how can I expect that you read the book if there's a very difficult test tonight? No, it's not that difficult, actually. No, I see you, Henry. No, I didn't recognize you with your hat on. Okay. Your thinking hat. Okay, get me one of those, please, too. There's not even a statistical distribution. There's just chaos. Okay. So some of you have the answer right. No, some of you definitely don't, D and E. And how are we going to do that? Let's see, is there anywhere yeah, there's the barium sulfate equilibrium, okay? Here's the barium sulfate equilibrium. I went through that, didn't I? So if you add sulfate, what would you do? You add sulfate to that solution. What would happen? You add barium chloride, what would happen? So what do you use? Water, sulfuric acid, or barium chloride? Why don't you discuss this with each other? Give me a revised answer, please. Come on, discuss it. You got to have it right. Not a very lively discussion, but a whole lot better than what I had this morning. It was like a graveyard this morning. I don't know if it was the weather or the fear of the exam or whatever. So you are relatively lively, especially at 1:30. It's pretty good, but not very accurate. You might be very precise, but precisely wrong, but not very accurate. Okay, so. But some of you know it. Why don't we go with C, okay? So the ones with C understood the common ion effect, or they should play the lottery today, because they are lucky. All right, so we have this equilibrium, and you have barium and sulfate is in equilibrium, and the constant is very, very small. That means we have very, very little of this here and most of this. And the common ion effect, if I have a relatively insoluble salt, and I put some of the ions, either one or the other of the ions in solution, I make it even more insoluble. Okay, I push it towards the left, the equilibrium. Now let's do that. Barium, let's see, sulfuric acid, I don't know if I start with sulfuric or with barium. I start with barium. Barium chloride is a very, very good electrolyte. It dissociates into barium 2+ and 2Cl-. So there's lots of barium ions available. It's very, very soluble. So what happens? I put barium into that equilibrium, so I push the equilibrium to this side. Okay? So that's not a good idea to dissolve this with sulfuric acid. Nevertheless, you could have thought sulfuric acid is a pretty wicked acid, and so if you get it on your skin, it burns very strongly, and it eats through your clothes from the battery acid. And now many of you don't know that anymore because the batteries are all sealed now, but in the old days you were working on your battery and suddenly you had holes everywhere in your clothes and in your jacket. And so this is a very corrosive acid. But it doesn't do it, all right? Because we have Le Chatelier's principle, and we have here the common ion effect. Now, the other common ion is I was talking about the sulfate here. I'm sorry. Okay, sulfate is that acid, so it goes the same way. You add this, you get to this. Okay. So with this, the only way to dissolve it was water. Okay, lots of it probably. So let's see, we have barium sulfate, and we are now talking about this equilibrium quite a bit. And the concentration of, and we add now, for example, 0.1 molar of sulfate. So the equilibrium concentration, this would be X and this would be X, okay? But if we want to add 0.1 molar, this would be 0.1 plus X, okay? 0.1 molar sulfate. So I want to know what is the concentration of the barium 2+ if I add 0.1 molar sulfate in solution. So this is how you do that. This is your solubility product, is the concentration of this, that's X, and the concentration of this, 0.1 plus X, and this is, what is it? It was about 10 to minus 11, isn't that right? Okay, so this is 1.1 times 10 to minus 10, okay? It's about 10 to minus 10. So how do we solve this now? We can say this is X squared essentially here, and no, 0.1 plus X. If I solve this, I get X is about 10 to minus 9, all right, because we have this 0.1 here. And you see the concentration change. What was it in equilibrium? What was the concentration in equilibrium? 10 to minus 5th. It went down by 4 orders of magnitude if I put in 0.1 molar sulfuric acid, okay? Good. So let's play a little bit more with heterogeneous equilibria. We have barium hydroxide. It's also a good electrolyte. It's totally dissociates into barium 2+ and 2 OH- ions. And sulfuric acid, I already told you, that is a very, very good acid. It dissociates in H+, 2H+, and SO4 2-. So if water by itself doesn't conduct electricity very well. Nevertheless, if you get a shock and you stand in water, that's not such a good idea, okay? Because you have a ground loop then, and you might die if you. So that's not it. So if your hairdryer falls into the bathtub, that's not a good idea, okay? That's why you have this ground fault interrupter on your hairdryer, okay? So you probably didn't know that, but don't dry your hair sitting in the bathtub, okay? All right. So this is about the conductivity of ions. Ions that are dissociated, these have negative and positive ions. They are conducting electricity, okay? And so if I now put barium and sulfate together, I form barium sulfate. And would it be soluble? No. Okay. So I put this barium hydroxide in the solution, and then I put some sulfuric acid in the solution. So suddenly I become less and less soluble, and it should conduct less and less, shouldn't it be? Okay. If I have this solution, a barium hydroxide solution, and I titrate this with sulfuric acid, so this will react with that to form insoluble barium sulfate. And what would also react? The OH- reacts with this to form water again. Okay, so that would not conduct very well. So let's have a look here. If I could have the camera, please, and the lights. Never do this at home. There is some open circuit here, and you see that light bulb has two electrodes, open electrodes pointing into the water here, okay? And so this is pure water. The light bulb is not on, okay? Now I'm going to use some barium hydroxide. What do you think? Should the light bulb go on or not? Because it will conduct between the two poles here now. And so I'm going to put that on here. Oh, there it is. See that? Was my switch, an ion switch, okay? So now it's on. Now I have in this burette here, why is this so blue? I have in this burette here sulfuric acid. I'm going to add sulfuric acid to this. What will happen to the light? A, B, or C? Why don't you give me your answer? What will happen to the light? If I titrate this with sulfuric acid, if I add sulfuric acid, will it do A, B, or C? Can you read it despite the light here? Can you read it in the back? Okay, good. Thank you. So what will happen? Why don't we do this, and then you're going to give me a new answer. But I'm not going to do the whole thing. I only do part of it. See, I could add as much sulfuric acid as I want here. I didn't limit this here, okay? So I have the sulfuric acid. If I could have the camera again, please. So I'm going to titrate this with sulfuric acid. Now I put the stirrer on here. Need my glasses, oh my God. Okay, and there is the sulfuric acid. And this is at 0. Let's put some, oh, you see the bottom there? What's happening there in the bottom? See that? Becomes milky. What is that? Precipitate. What is the precipitate? Barium sulfate, okay. Lots and lots of barium sulfate. I'm precipitating the barium with the sulfate now. You notice the light? Okay, it's still a little bit on, huh? But I would consider it's nearly off, huh? Okay. All right. So why don't you give me your answer again? Discuss it with each other and give me the answer. Is it A, B, or C? I'm not necessarily stopping. I'm not done necessarily, okay? What is it? So the light's nearly off now. So was it this here, that here, or this one here? Okay, why don't you all click in, have your discussion abbreviated. I need to solve that mystery for you. Another 10 seconds I give you. Okay, everybody click in. So what do you think? Aha. So this is totally wrong here. A is totally wrong. B is wrong too. C is right. Okay? So watch, okay? Can I have the camera again, please? So what happens here? It is B, okay? It is B. I'm sorry, I did it wrong here. It is B. Of course, you have, what you have here, here's the barium sulfate totally precipitated. That's when I had it dark. And now you're adding just sulfuric acid. Did I say C? Ah, that was wrong. I added sulfuric acid, and now you have just the H2SO4 dissociated. It's a strong electrolyte, and with this you had it B.